So guess what we talk about today?
Dividing.
Right. So we're actually going to, there are two types of problems. We're going to start with the pretty basic one, and then we're going to talk about a little more complicated one. And we're going to go down memory lane to back to 4th grade. After that, right, yes. Now, so first problem, we're going to divide. Now, here's, I'm going to call this the basic division problem. So our basic division problem looks like this. I'm going to give you 5x squared y minus 10xy plus 15xy squared 5xy. This is, I call this your base, this is a division problem. You might say, well, no, that's a fraction. Well, that's the same thing, because this is called a division bar. It means this divided by this. So here's a division problem. I call this a basic division problem because the denominator is only one term. It gets a little more complicated when the denominator is more than one term. But first, we're going to deal with, how do you deal with it when it's just one term? And anytime you have a fraction with several terms on top and one term on the bottom, you can break it apart. And what I mean by break it apart is I can break this apart into 3 little fractions where it's equal to 5x squared y over 5xy minus 10xy over 5xy plus 15xy squared over 5xy. It's this whole idea. I mean, like if you have a common denominator, then you could put it all under one denominator. But I'm going backwards. So anytime you have a big ugly fraction with a single term at the bottom, you break it apart. And now you have 3 little problems. And these 3 little problems are pretty easy. They kind of reflect what we did on Wednesday. As far as our 3 little problems go, okay, well, the 5's are going to cancel, or this x cancels one of those x's, and the y's cancel, so I'm just left with an x. Over here, well, this 5 makes that a 2, and these x's cancel, these y's cancel, and so that just gives me a negative 2. And let's see, 15, 5 goes into 15 3 times, this x cancels this, and this y cancels one of those y's, so that's going to give me a plus 3y. And I've done the division. Is that right? So anytime you were dividing by a single term, say, oh, that's fine. I mean, it's a fraction, so I'm just going to break it apart into its little parts. Right? So, your turn. What if I give you, I'm going to start further over here so I've got some room, 9x cubed y cubed minus 18 x squared y squared plus 21 x squared y cubed all over 3x squared y squared. So this one breaks up into its little parts. So if I break this up into little fractions, that's going to give me 9x cubed y cubed over 3x squared y squared minus 18x squared y squared over 3x squared y squared plus 21x squared y cubed over 3x squared y squared. And you simplify each fraction. So let's see, 3 goes into 3 times. That's an x cubed, so this cancels all. I've got 1x left on top, and I've got 1y left on top, so it's going to give me a 3xy. 3 goes into this 6 times. The x squareds cancel, the y squareds cancel, so that's just going to give me a minus 6. And let's see, 3 goes into 21 7 times. The x squareds cancel, and this cancels all but one of the y's. And so I end up with a plus 7y. Everybody okay with this? Right? So this is the basic division, right? So like we talked about, like yesterday it was adding, subtracting, multiplying polynomials. So now, I mean, technically this is dividing polynomials. This is a polynomial and this is a polynomial, although it's only one term, so there's not much to it, right? So how do you divide polynomials that are a little more involved than this? Well, that's what we're going to do today, but before we talk about that, I want to go back to 4th grade math. And please don't write this down. My job is not to teach you 4th grade math. I need to make some reference to it. So here is my 4th grade math problem. My 4th grade math problem is 31 into 2594. There's my 4th grade math problem. Long division. Yay, right? So, see, let's just talk about, I'm just going to tell you how I was taught how to do this problem. So, how do you do long division? Well, you think, okay, how many times does 31 go into 259? And I'm like, and my teacher said, you know, trying to figure out how many times 31 goes into 259, that may be harder. What you can do, and it works most of the time, is instead of figuring out how many times 31 goes into 259, ask yourself how many times 3 goes into 25. That number's a little more manageable. And most of the time it works. That's what my teacher told me. So that's what we're going to do. I'm going to look at this, and I'm going to ask myself, instead of asking how many times 31 goes into 259, I'm going to ask how many times does 3 go into 25. And so what's that number going to be? Like 8? 8? Right? Like our goal is, right, like whatever number I put here, and I know some teachers get picky about like placeholders or whatever, but to be honest, it doesn't matter. Just put some number up here. So I'm going to, and my goal is I wanted 8 times 3 to get really close to 25, right? Whatever I put here, this times this has got to get close to 25 without going over. All right, so I guess 8, so I'm going to do 8 times 3 is going to give me 24. 8 times 1, that gives me 8. All right, and then my 4th, you know, then you subtract. All right, fine, subtract, and that gives me what, 11. And you bring the 4 down, and now you kind of do this whole process again. You ask yourself what goes here, right? So that this, you know, this times this gets really close to 11. Right? I mean, I could say this times 31 equals 114, but I mean, 114, but yeah, it's harder to think about. Let's just think about how many times, what needs to go here so that this times 3 gets us close to 11. So what's that number going to be? 3. So I put the 3 here, and 3 times 3 gives you 9. 3 times 1 gives you 3, right? And then when we subtract, I think that gives us 21, right? Yeah. And then in 4th grade, they would do something like we'd call that the remainder, right? And then in my 5th grade class, we did the advanced version of it. And the advanced version of it wasn't good enough just to say this had a remainder of 21. You had to say this is 83, and then this is 21 31st, where you actually take the remainder and put it over this. All right? And the end result is, if you multiply this thing times this number, you get this number. That's how this whole division process works, right? So, was this close to what you did in 4th grade? For me, it was 4th grade. I don't know what it was for you guys. All right. 4th or 5th grade, definitely elementary school, right? Okay. All right, so why did I talk about this? Well, the reason I talked about this is we're actually going to do long division, but with polynomials. See, write this down. Let's do x plus 2. And let's do x cubed plus 10. And the beauty of polynomial long division is you do exactly what you did in 4th grade, except it's easier. Okay? All right, just hear me out, all right? Like, remember how you had to kind of guess a little bit? Like, we had to do a little bit of thinking to figure out what goes here? You could do significantly less thinking when you're doing polynomial long division. And here's how it works. So back here, remember we were thinking how many times does 31 go into 259? And we didn't really look at the 31. We just asked ourselves how many times does 3 went into 25? And our goal was we wanted something up here so that this times the 3 got pretty close to 25 without going over, right? And that's the thing. You had to do a little bit of thinking. Well, in polynomial division, log division, you don't have to get close. You want it exact. So think of this 31, or think of this x plus 2 as like our 31. And think of this 25 as this x cubed, and you think of this 5 as whatever this term is, right? And here's how it works. I need something here so that this times this x is exactly x cubed. And so what's going to go here so that this times this is exactly x cubed? X squared, right? Everybody okay with x squared? And so I'm going to put an x squared. And yeah, I know I'm going to get a lot of pushback that I technically should put the x squared here, but it really doesn't matter. Just stick it somewhere up here. So I'm going to have x squared, and so now I do x squared times x, which is going to give me x cubed. And remember, when I put the 8, I didn't just multiply the 8 times the 3, I also had to multiply the 8 times the 1, didn't I? Right? So that means I have to multiply the x squared times the 2, and so that gives me plus 2x squared. Right? What's important is you see that I'm kind of doing the same thing I did here, just with some letters. All right, now what did I do with the 248? What was the next step? I subtracted, right? All right, so we're going to subtract. Now, the thing you've got to remember, whenever you subtract some sort of polynomial, that just means you change your signs. All right? So we're going to change the signs. Like this subtraction means, okay, this is a minus, and that's going to change that plus to a minus, right? Now combine, and here's what happens. These cancel, right? This first term is always going to cancel. If it didn't cancel, you made a mistake. So this cancels, and then I get 11x squared minus 2x squared. That's going to give me 9x squared. Okay, that's where I got the 11. What did I do next? I brought down the 4, right? So what am I going to do here? Bring down the negative 10x. And now we start the process all over, right? We think about something here so that this times this exactly equals this. And so what's going to go here so that this times this exactly equals 9x squared? 9x. So I'm going to put a plus 9x, and now we start. This times this gives me 9x squared. This times this gives me a plus 18x, right? And now what do? You subtract them. Let's see, I subtract. And when you subtract, that's just when you subtract a polynomial, that you just basically change all your signs. So that plus now becomes a minus. And this cancels because, well, it has to. When I combine these, this gives me a negative 28x. I'm going to bring down the 6. And then I got to think of what goes here. So that this times this is exactly negative 28x. So what has to go here? Well, negative 28, right? Because it's got to match exactly. Because negative 28 times x gives me a minus 28x. And the negative 28 times 2 is a negative 56. And now we have to subtract this, which in polynomial terms means change your signs. So I change my signs, and oh, that cancels because it has to every single time. And then we're left with 62, and that's our remainder. Yes?
Wait, so you changed, when we subtracted 9x squared from 9x squared, so like originally, you switched it to subtracting in the middle because
well,
you subtracted it.
So here's what was originally put there.
Yeah.
And since there was a negative in front, that negative in front means I have to change all the signs.
Oh, okay.
And then add. All right.
Okay.
All right, so I get a 62. That's my remainder. What did I do with my remainder over here?
Put it over the 31.
I put it over the 31, right? And so guess what I'm going to do with my remainder here? I'm going to put it over the x plus 2. So that's going to put a plus 62 over x plus 2, and that's our answer. We have successfully done polynomial long division. And what is polynomial long division? It's the exact same thing you did in 4th grade. But for me, I actually think it's easier because I don't have to think as hard. Because like with the 8 and the 3, there's a little bit of processing that goes on. You're not doing as much processing. You're saying what goes here so that this times this exactly equals. I'm not trying to get close. I'm trying to get exact. All right, your turn. Yes. Yes. Okay, so I want you to do x minus 1 into x to the 4th minus 3x cubed plus 2x squared minus 4x plus 4. And I'm going to hit. Okay, so now we ask ourselves, what goes here so that this times this exactly is x to the 4th? X cubed. All right, so I get an x cubed, and this times this gives me x to the 4th. This times this gives me a negative x cubed. Then we subtract, which means we change the signs. And so this cancels because it has to. And that gives me a negative 2x cubed, and I'm going to bring down the plus 2x squared. And we start the process over. What goes here so that this times this exactly equals negative 2x cubed? Negative 2x squared. So I'll put a negative 2, oops, what did I keep this kind of color-coded? Negative 2x squared, so now this times this gives me a negative 2x cubed. This times this gives me a plus 2x squared. And when we change the signs, oh, that's different. What happens? Everything cancels. Well, that's not what I was expecting, right? Because, you know, just kind of follow through. So what do? Well, we bring down stuff. I'm going to bring down a negative 4x, and I'm going to need to bring down another thing. So I'll bring down the negative 4x plus 4. Sort of bring down whatever you need. I mean, technically, like when I brought down this 10x, I could have also said this is a 10x plus 6, but I didn't need the 6, so there's no point in writing it down. If I've got 2 terms here, I'm going to need 2 terms here to kind of do the whole process. Since I got rid of everything, it says, all right, well, fine, I'm just going to pull down the next 2 terms. And we still start the process again. I put something here. I've got to think, this times this exactly equals negative 4x. So what has to go here? The negative 4. So this times this gives me a negative 4x. This times this gives me a plus 4. And when I change the signs, what happens? Everything cancels out, and so we get a remainder of 0. Right? You're allowed to have a remainder of 0. Okay? It happens. You know what it means if you get a remainder of 0? That means this thing times this exactly equals this. And in the very near future, it's going to be a very good thing that we get a remainder of 0. We're going to be able to use that in all sorts of interesting ways. But today, it's all about how do we divide. Sometimes you get a remainder, right? That's how you deal with it. Sometimes you don't get a remainder, and that's fine too. And so you get your answer. Meaning, had I given you this thing times this, and you multiplied it out, you would get exactly this. And one more before I start doing tricky stuff. I just want to make sure we're all comfortable here, right? And to be honest, I'm making this up, so there's a reasonable chance that the numbers turn out ugly. Well, let's say if I give you x minus 3. Oh. Let's say I give you x cubed plus 4x squared plus 5x minus 7 over x minus 3. This is a division problem, right? Anytime you see a fraction, that's a division problem, right? It's this divided by this. Okay. So how do you solve it? Well, if it looks like this, you write it as x minus 3. I'm going to divide that into x cubed plus 4x squared plus 5x minus 7. And I'll let y'all finish. So, same question, right? What goes here so that this times this exactly equals x cubed? X squared, right? And so this times this is going to give me x squared. This times this gives me a negative 3x squared. And then we change the signs because we're subtracting. And so now I end up with 7x squared plus 5x. And we think about what goes here so that this times this exactly equals a 7x squared. 7x. And so this times this gives me a 7x squared. This times this gives me a minus 21x. And we change the signs so that cancels. Lovely. That's what happens when I make up something. And so now I get 26x minus 7. And then I need to think what's going to go here so that this times this exactly equals this.
26.
26, yay. This times this gives me 26x. This times this 78. So negative 78. And now when I change the signs, this cancels, and 78 minus 7 is a 71. There's my remainder. So I'm going to put plus 71 over, oh, whoops, 71 over x minus 3. We're going to add it. Yes?
Okay, so when you're adding like the 4x squared and the 3x squared, would you not combine the exponents?
So the only time exponents change is when they're multiplied.
Oh, okay.
Right? So like on Wednesday, we dealt with everything was being multiplied, and so exponents change. Exponents never change when you're adding.
Okay.
And that was not a silly question because I'll guarantee there are at least 5 other people that needed to hear what I said. So. All right. So, let's see. Need to do some interesting questions. All right. Well, what if I gave you, let's do x cubed minus 5x plus 2 divided by x plus 4. I just have to show all the ways that you could divide, right? Because that's kind of elementary school-ish, right? They're not going to say this. Right? They're going to say this. Even this is kind of elementary school-ish, but I have questions like that. So. All right, well, okay, so this divided by that means I'm going to put x plus 4 into x cubed minus 5x plus 2. So I'll give you, just see what happens when we start, right? So it starts the same way. You think, okay, what goes here so that this times this exactly equals x cubed? So x squared. That's just like the other problem, right? So I'll put an x squared here, and so this times this is going to give me x squared. This times this is going to give me a plus 4x squared, right?
X cubed.
X cubed, oh yeah, this one's x cubed, yes, thank you.
Oh.
Yeah, right, so far, so good? And then it's not like the other problems, is it? Like this cancels like it's supposed to, but this doesn't because there aren't like terms, right? So great job realizing they're not like terms, right? So what we have to do is, well, how do we make this look like the other problems? And here's how we do that. We basically take this stuff here and shift it to the right because we need like an x, like your complaint is there's no x squared term here, right? So how we deal with that is actually there is an x squared term here. So what's it? This is minus 5x plus 2. There is an x squared term here. It just happens to be plus 0x squared. Isn't 0x squared the same thing? I mean, I haven't changed the problem any, have I? Just basically added a 0. Oh, but now things look like they're supposed to, right? So we can continue the problem.
Wait, but how do you just add something randomly?
I can always add 0, right?
Equals 0. But the x squared.
0 times x squared is what?
0. He just moved the -5 over to an x step.
Because I needed things to line up, right? Like this whole process depends on position, like things lining up. Okay, so now we change the signs. And when I add, let's see, this cancels because it's supposed to. This is going to give me a negative 4x squared minus 5x. And I want to go up here and I think, all right, what goes here so that this times this is exactly negative 4x squared?
Negative 4.
Put a negative 4x. So I get a negative 4x, so this times this gives me minus 4x squared. This times this gives me a minus 16x. Now when I change the signs, because I'm subtracting, this cancels because it's supposed to. And this gives me 11x, and I'll bring down the plus 2. And now I think what has to go here so that this times this is exactly 11x? 11. Okay, so fine. I'm going to put a plus 11. And so that gives me 11x plus 44. And when I subtract it, it means change this sign and change that sign. This cancels because it's supposed to. I get a negative 42. And with that negative 42, that's going to be minus 42 over x plus 4. And here is my answer. All right, what's the takeaway from this? When you are doing long division, these exponents have to go in order. Like note the first few problems I gave you, they went down in order. There was an x cubed, squared, whatever, right? If you're ever missing one, put a placeholder in. Like I was missing the x squared term. And you notice it didn't work, right? So for this procedure to work, put a placeholder. Do you actually technically have to put 0x squared? No. If you wanted to, you could just shift everything over so it still lines up, right? A lot of textbooks tell you to put a 0x squared in, so that's why I'm telling you. Just realize that you have to move things over. So this is long division. What's the goal for the day? The goal for the day is when you do polynomial long division, I want you to realize it's the exact same thing you did in elementary school, right? If you at the end of today, you're looking at polynomial long division and you say, oh yeah, that's the same thing I did in elementary school, you're going to remember how to do it, right? And I wanted to, that's why I started it from that sort of perspective. All right, so I'm going to go ahead and stop.